All right, Calc AB. Today we're going to focus on area and volume. So first we're going to look here at part A, which is find the area of region R. So region R is bounded by the curve f of x equals square root of x plus 1. And g of x is the curve x plus 1, or the line x plus 1. So find the area is just the integral of the top minus the bottom. So we're going to go the integral from -1 to 0. That's the left side at -1 to the right side at 0 of top, which is square root of x plus 1, minus the bottom, which is x plus 1, which you need to make sure you subtract the whole thing there, dx. And so if we calculate the integral of that, we get x plus 1 to the 3/2. And we need to balance that with the 2/3 out front. Minus 1/2 x squared minus x from -1 to 0. Plug in 0, you're going to get 2/3. And then minus 0 minus 0. Minus plug in -1, you're going to get 0 for that first term, and then minus 1/2 plus 1, which will be 2/3 minus 1/2, which is 1/6. So the area of the region R is 1/6. Now, as a little side note, you could also do that area in terms of y. So if you wanted to do the area in terms of y, you could here also. And to do that, your integral is from the bottom y value of 0 to the top y value of 1. And then you would do right minus left as opposed to top minus bottom. So right minus left would be x plus 1 minus the square root. Nope, sorry, just kidding. If we're doing dy, we have to be in terms of y. So we need to write these in terms of y. So this is y squared minus 1. And this becomes x equals y minus 1. And so now we're going to do line minus curve, or right minus left. So y minus 1 minus y squared minus 1 dy, which you could calculate, and you would get the same answer of 1/6. So that's how you could do that in terms of y. All right, part B, find the volume of the solid generated when R is rotated around the x-axis. So the x-axis is here. And so if we rotate it around, it looks like this. Okay, but that's a whole lot of mess on our paper. And so if we focus on where the line of rotation is, which is right here, we know that the big R, the radius of the outside circle, is going to follow around from the outside of the curve to the rotation. I'm going to color this in so we can see what goes in the curve and what goes out of the curve, or the region, sorry. So the big radius goes from the outside of the region to the line that you're rotating around. And then the small r, the inside, the kind you're subtracting out, goes from the inside. So big R is going to be between the curve and the x-axis. So that's just going to be the square root of x plus 1. And then little r is from the line to the x-axis. So that's going to be x plus 1. And then the formula for this is the washer method. So the big washer is pi r squared. The little washer is pi r squared. So it's pi r squared minus pi r squared. So we take the pi out. We're going -1 to 0 of big R squared minus little r squared, all in terms of x, because we're going to stack these washers along the x-axis. And then we're going to calculate this one also, and then after this we're going to just set up a do not solve. And so this is going to be pi -1 to 0 We're gonna have to multiply this out first. This will be x plus 1 minus x squared minus 2x minus 1 dx, which is pi times the integral of -1 to 0, negative x squared minus x, which is pi out front. Don't forget your pi. -1/3 x cubed minus 1/2 x squared from -1 to 0, which is pi times, when you plug in 0, you get 0, minus, when you plug in -1, you get 1/3 minus 1/2, which is 1/6 pi, or pi over 6. All right, part C, write but do not solve when you find the volume by rotating around the horizontal line y equals 3. So again, on most of these AP problems, you're going to be way off the page, and then it's going to be up here, and this would be a huge mess on your paper. And so we really just want to think about, if we were to draw this line way up here at y equals 3, then we would have our big radius from 3 to the outside of our region, and our little radius from 3 to the inside of our region. And you can just draw that, and that'll give you a visual for your big R and little r. So big R is between 3 and the line, and we're still doing dx. So this is 3 minus x plus 1, which we could simplify to write -x plus 2. And then little r is between the line 3 and the curve, so 3 minus square root x plus 1. And then, so we're going to take the integral from -1 to 0 of pi r squared minus pi r squared. So we're going to factor the pi out. So -x plus 2 squared minus 3 minus root x plus 1 squared dx. Okay, now same thing around the horizontal line y equals -1. So we are still in the dx world. And so if we rotate down here at -1, our big R is between the line we're rotating it around and the outside of the curve. Our little r is between the line we're rotating it around and the inside of the curve. And so big R is top minus bottom. That's going to be curve minus -1. So the curve is square root x plus 1 minus -1, or square root x plus 1 plus 1. And then little r is between the line is on top, so x plus 1 minus -1, or x plus 2. So the most important thing, the hardest part, is getting big R and little r, and then it's pi r squared minus pi r squared, factoring out the pi. Integral from -1 to 0, square root x plus 1, all squared, minus little r squared, which is x plus 2, squared dx. Okay, part E, we are now rotating around a vertical line. So that's going to change this into dy. So we're going to rotate around the vertical line of x equals -2. That's over here. That means it's going to look like this over here, and this big rotating it around. But again, that makes a mess. So we are just going to draw our big radius is from the line to the outside of our region, and the little radius from the line to the inside of our region. And so big R, now we're going to have to do right minus left, and we're going to have to do everything in terms of y, because we're going to stack those washers up and down the y-axis. So we're going to stack this way, and so we are dy everything. So we need to do right minus left, because the right side is bigger than the left side. So we're going to do line minus -2, but we need it in terms of y. So big R The line is y minus 1 minus negative 2, or y plus 1. And little r is the curve minus negative 2. So y squared minus 1 minus negative 2, or y squared plus 1. And so now we're going to integrate, but everything's going to be in terms of y. So we go from y equals 0 up to y equals 1, pi r squared minus pi r squared. So pi out front, y plus 1 squared minus y squared plus 1 squared dy. All right, now we're going to rotate around x equals negative 1. I suggest you go ahead and pause and try to do that one on your own. All right, so now hopefully you have unpaused and you can check your work against mine. So for F, we got that. All right, moving on. So those are just rotating it around, finding the volume, and now we're going to focus on a couple of cross sections. So that's when we build up onto this base. So this region is the ground. Okay, this is your concrete base. So on part G, we are going to put cross sections up perpendicular to the x-axis, and it's going to be a rectangle whose height is 4 times the length of the base. So when we do this, we need to automatically draw a base perpendicular to the x-axis. So that draw a line in the region perpendicular to the x-axis, and that is the base of our rectangle. The rectangle then is standing up from there. So that is standing straight up, coming out at you. So we need the base is going to be the distance between the two curves, and we're going to do top minus bottom. This is perpendicular to x, so it's dx. So the base is the square root of x plus 1 minus x plus 1. And then the area of this rectangle is going to be base times height. And so we need the height. And we were told that the height is 4 times the base. So the height is 4 times square root x plus 1 minus x plus 1. And so for cross sections, we do the integral from a to b of the area in terms of x, or we do the integral from c to d of the area in terms of y times dy. So you just need the area, and the area is base times height. And so this is going to be the integral from negative 1 to 0 of the area, which is base times height, which is going to be this times this. So notice that big mess is repeated. So we're going to say this is 4 times square root x plus 1 minus x plus 1 squared. Base times height, dx. All right, then the question says, well, what if instead we made it an isosceles right triangle? So we could draw, this now is not the base of a rectangle, it is now the side of a right triangle. So that's now the base of the right triangle, and so the base is the same. Okay, the b is square root x plus 1 minus x plus 1. The height is the same because it's an isosceles right triangle. The area of a triangle is 1/2 base times height. And so this is the integral from negative 1 to 0 of 1/2 base, which is square root x, that should say plus 1, minus x plus 1 times the height, which is that same thing, so squared dx. So that's what it would look like for an isosceles right triangle. All right, H. Same region, except now the cross sections are perpendicular to the y-axis, and they're going to be a semicircle. So now we need to draw perpendicular to the y-axis, and that's going to be a semicircle. So the area of a semicircle is 1/2 pi r squared, half of a circle, and r is going to be halfway between the two curves. And since we're perpendicular to y here, we need everything in terms of y. And so that's going to be, radius is half of right minus left. So the radius is half of right, which is the line in terms of y, so my y minus 1, minus the curve, which is y squared minus 1. And so that is your r, which we could simplify a little bit as 1/2 times negative y squared plus y. So the area is 1/2 pi, and then r squared, and r is 1/2 negative y squared plus y. So all that squared. And so we have the integral from 0 to 1, because we are in y, 1/2 pi, radius, which is 1/2 negative y squared plus y, all squared, dy. All right, part I, the vertical line x equals k divides r into two regions with equal area. So I'm going to erase what we have here. And I'm going to color our region again. And we need to figure out a vertical line x equals k that splits this area up equally. Half on the left, half on the right. So we've got some k, maybe here-ish, that splits up that area evenly. So if you go back to part A, we know the area of the whole thing is 1/6. Half of 1/6 is 1/12, so the area here is 1/12, and the area here is 1/12. So we're going to focus on this half over here. And we're just going to set up an integral for that. So the integral is going to be the integral from -1 to k is curve minus line. So square root x plus 1 minus x plus 1 dx. And that's going to equal, that area will equal 1/12. So that's just setting up that equation. Okay. Notice it says set up an equation, which means it needs an equal sign as opposed to setting up an expression is what we've been doing. All right, part J, same thing, except a horizontal line. So we're going to split the area in half again. Except we're going to do the area this way. So we're going to have some h this way. And so this area is 1/12. And so we need to do it in terms of y. And so the way I have that set up, the part I shaded, that is the integral from h up to 1. And you need to do the right minus the left. So y minus 1 minus y squared minus 1 dy, that's going to equal 1/12. And so that's all you had to do was set those up. All right, there's your super free response on area and volume. Hope you enjoyed it.